Ask anyone what's waiting for you inside a black hole, and you'll hear the same answer every time: certain death, no exceptions. But the equations describing that cosmic trap hide something else, something that looks, on paper, disturbingly like a door. Deep inside the mathematics of gravity, a falling traveler seems to approach another region of space, another point in time, or a universe that isn't ours at all. Science fiction borrowed this idea rather than inventing it. General relativity put the bridge there first, decades before anyone used it as a plot device. Here's the honest answer. Right up front, mathematically, black holes can resemble portals. Physically, no known black hole has ever offered a passage that anything could cross and survive. That gap between the door equations keep drawing and the door nature refuses to open is the whole story this video is about to tell. So the real question was never whether black holes are strange enough to hide a portal. It's whether anything could actually survive the crossing and arrive somewhere else. Picture drifting toward a perfectly black sphere, wider than an entire solar system, with no wall, no hull, no physical surface waiting to stop you. Only an invisible boundary separates the universe you know from a future that can never be undone once you cross it. For a black hole massive enough that crossing might not even announce itself, your instruments keep working, your heart keeps beating, and the stars behind you stay visible for a while longer. Nothing local marks the exact instant your escape disappears. There's no flash and no visible scar, so you just have to trust the math instead of your own senses. From that instant on, every direction you could steer now leads deeper inside. Turning your engines around does about as much good as trying to fly backward out of tomorrow. Outside the horizon, moving inward is still a choice you make. Cross it, and inward stops being a direction through space and becomes a direction through time instead. That shift is the real definition of a black hole. Less an object floating in space, more a place where space-time itself leans irreversibly toward an ending. Most people picture that ending as a single point, a singularity, where infalling matter gets crushed by gravity until the story simply stops at infinite density. Classical general relativity does predict singular behavior under a wide range of conditions, though the exact shape of that interior depends on the black hole and whatever disturbs it along the way. An infinity showing up inside an equation usually just means the theory has hit the edge of what it can describe, not that nature literally contains an infinitely dense point. A singularity, then, might be less a real destination and more a warning label. Gravity's way of admitting it has pushed the geometry past what Einstein's equations can safely explain. Quantum mechanics almost certainly matters down there, since no experimentally confirmed theory yet unites it with gravity in that extreme regime. And that blank space in our knowledge is exactly where portals, baby universes, and cosmic rebounds all find room to exist on paper. A gap in our knowledge, though, is never proof that any single one of those possibilities is actually real. To see where the portal idea actually came from, go back to the moment black holes first turned into mathematical objects rather than speculation. In Einstein's equations, gravity isn't some invisible force reaching across empty space. Matter bends space-time, and that curved space-time then guides everything else along paths we simply experience as falling. Pack enough mass into a small enough space, and those paths bend so sharply that every route pointing toward the future ends up pointing inward. Carl Schwarzschild worked this out in 1906, finding the first exact solution for the space-time surrounding a spherical mass, barely months after Einstein published general relativity itself. His solution contained one suspicious radius where the mathematics seemed to break down completely, and physicists spent decades arguing over what that really meant: a genuine physical disaster or just an artifact of the coordinates being used. Better mathematical tools eventually settled the argument. The boundary itself, it turned out, could be crossed smoothly after all. The real breakdown sat deeper inside the idealized solution, and extending the full geometry revealed something nobody expected: two separate exterior regions, each looking like its own universe, joined by a connection running through the middle. In 1935, Albert Einstein and Nathan Rosen studied exactly that kind of geometry: two sheets of space-time stitched together by a bridge running between them. That structure earned the name Einstein-Rosen bridge, and it's the direct mathematical ancestor of everything we now call a wormhole. From the outside, each entrance looks like an ordinary black hole, with a throat between them shaped by bending space itself rather than drilling through it. Two destinations separated by unimaginable distance can end up as next-door neighbors once you account for the hidden geometry linking them. It's tempting to picture this the way you'd fold a sheet of paper to press two distant points together, creating an obvious shortcut between them. But spacetime isn't a sheet floating inside some bigger ordinary room, and no tunnel gets carved through any external material to make this work. It's the geometry itself. Doing the rearranging, distance folding from the inside, which sounds exactly like a portal because mathematically, that's precisely what a connection between separated regions is. One fatal detail ruins the trip. The original bridge simply doesn't stay open long enough for anything to cross it. Its throat pinches shut faster than light itself can travel from one exterior side to the other, let alone a spacecraft. So entering through one mouth never leads to some dramatic emergence beneath alien stars. A traveler's future still runs out inside the black hole, just like it would anywhere else past the horizon. No engine, however powerful, can outrun that collapse, since the limit has nothing to do with thrust or speed and everything to do with causality itself. Even light, the fastest messenger relativity allows, can't finish the crossing before the throat seals. 2 points can be next-door neighbors on the map and still be separated by an uncrossable wall of time. That's the trick this bridge never manages to solve. That second exterior only belongs to an eternal, perfectly undisturbed black hole, not the kind any collapsing star actually leaves behind. Real matter and radiation start perturbing the geometry almost immediately, and the clean portal-like structure is usually the first thing to go. Physicists didn't abandon the idea of actually crossing a wormhole, though. They just asked a more ambitious question instead: could some form of matter hold the throat open against gravity's pull? In 1988, Michael Morris and Kip Thorne worked out exactly what a humanly traversable wormhole would require: a throat with no event horizon, tidal forces gentle enough to survive, and enough long-term stability for a traveler to actually make the return trip. Ordinary matter can't provide any of that, since its positive energy makes gravity attractive by nature, which just encourages the throat to collapse instead of staying open. Keeping a traversable wormhole open within ordinary general relativity means using stress energy that breaks the usual energy conditions physicists rely on everywhere else. That kind of support usually goes by the name exotic matter, something with effectively negative energy density, at least in the right configuration. Negative energy isn't just a fantasy invented to rescue a convenient equation. Either quantum fields really can produce limited situations where energy dips below the level of the surrounding vacuum. The Casimir effect is the famous real-world example, quantum physics quietly permitting an energy arrangement that classical physics would call impossible. A tiny lab-scale quantum effect, though, is a long way from a stable tunnel wide enough to fly a spacecraft through. Known physical restrictions seem to cap how much negative energy can exist at once, how long it can last, and how tightly it can be concentrated in one place. A wormhole throat might simply demand more of it, or a different arrangement of it than nature is willing to provide. And even if the right material existed somewhere, actually building the tunnel would be an entirely separate problem. Equations can describe a wormhole that already exists without ever explaining how a civilization would go about manufacturing one. Expanding even a microscopic opening might trigger enormous quantum effects or simply destroy the geometry before it becomes large enough to use. Any portal capable of shortening interstellar travel would also create a dangerous relationship between space and time, whether anyone intended it or not. Move one mouth at high speed, park it near extreme gravity for a while, then bring it back to reunite with the other, and the two clocks may no longer agree with each other. At that point, the wormhole could become a path leading into the past, relative to whoever's watching from outside, turning a shortcut through space into something closer to a machine for breaking cause and effect. Stephen Hawking proposed in 1992 that some deeper law probably prevents these time machines from ever becoming usable, an idea he called chronology protection. Quantum fluctuations, in his picture, would grow explosively right at the moment a time loop tries to form, destroying the wormhole before the loop closes. The exact mechanism behind that protection is still unsettled, mostly because testing it properly would require physics we don't yet have access to. Every door tried so far has slammed shut, but there's one shape of black hole we haven't tried yet, and it looks far more promising than the rest. Most black holes in the real universe aren't perfectly still or perfectly spherical. Stars rotate before they collapse. That spin carries over as angular momentum, and the black holes left behind should keep spinning too. Rotation changes the mathematical interior dramatically, and a spinning black hole is described instead by the Kerr solution, worked out by physicist Roy Kerr in 1963. Instead of crushing everything down to a single point, the idealized Kerr geometry contains a rotating ring, and its full mathematical extension includes inner horizons plus pathways leading toward other regions of spacetime entirely. Some of those paths appear to slip around the ring and continue on into another universe, or another distant region just like ours. Here, the portal idea comes roaring back with far more force than before. A traveler might cross the outer horizon, navigate the rotating interior, and emerge through a completely different exit. The exact solution even permits stranger routes still, ones where ordinary ideas about space, time, and cause and effect get distorted almost beyond recognition. The Kerr interior, unfortunately, is just as perfect a mathematical construction, and just as unrealistic, since real black holes are never actually isolated from radiation, dust, gravitational waves, and the faint background hum of the rest of the universe. Near the inner horizon, streams of energy falling in and streams still trying to escape can collide at extreme relative speeds, and their combined energy grows enormously for anything caught falling along with them. Physicists call this process mass inflation, and it can drive curvature up so violently that the smooth inner gateway gets replaced by a destructive, singular mess. A path that exists cleanly in the untouched Kerr diagram vanishes almost the instant a realistic disturbance gets added back in, which is exactly why current research treats this inner horizon instability as one of the biggest obstacles to any portal-like passage through a rotating black hole. Nature seems to attack the doorway precisely where the ideal equations make it look most tempting. The slower the incoming material moves, the more extreme that counterstreaming becomes near the inner horizon. Instead of opening into some calm second cosmos, the interior may end up behaving like a particle accelerator with no safe chamber waiting at the far end, radiation and curvature far beyond anything ordinary matter could survive. Long before you'd ever reach the horizon, the environment around many black holes is already lethal on its own. Around actively feeding supermassive black holes, the glowing accretion disk alone can outshine the entire host galaxy. Magnetic fields launch jets of particles thousands of light years long, punching straight out of the galaxy. High-energy radiation tears atoms apart just outside the horizon, long before gravity gets the chance to. A quiet, isolated black hole would obviously be a safer approach, but calm surroundings outside do nothing to fix the geometry waiting within. Size, at least, can delay one particular kind of destruction, even without solving the portal problem itself. Small black holes generate brutal tidal forces right at their horizon, pulling your feet inward far faster than your head and stretching your whole body in a process nicknamed spaghettification. A supermassive black hole, by contrast, can have tidal forces gentle enough at the horizon that crossing it might leave a traveler perfectly intact for minutes, hours, or even longer, depending on mass and trajectory. That survival, though, would only ever be temporary. Push deeper inside and tidal forces start climbing again, escape stays impossible the whole way, and every route you're allowed to take keeps approaching the region where known theory simply gives out. From your own perspective, crossing the horizon takes a perfectly finite amount of time. Nothing dramatic about the clock at all. A distant observer sees something stranger. Your signal red shifts and fades, seeming to freeze near the boundary forever, even though you never actually stop. And that's the catch for any hidden portal. Whatever's on the other side could never send confirmation back to the same entrance, so no exit has ever been confirmed from out here. Astronomers do watch compact objects swallowing gas, bending light, colliding, and ringing through gravitational waves. And every one of those signals lines up closely with what general relativity predicts for ordinary black holes. None of it requires matter to reappear anywhere from a second mouth. A portal could still be hiding behind the horizon, sure, but an invisible possibility only ever explains everything by explaining nothing you can actually test. What science needs is a prediction sharp enough to tell a portal apart from an ordinary black hole. Maybe material entering one object could emerge somewhere else through a white hole, essentially a black hole running in reverse, where nothing can enter from outside and only matter and light are allowed to come out. General relativity does permit white hole regions inside certain extended solutions, at least on paper. The universe hasn't offered any convincing evidence that astrophysical white holes actually exist out there, and their behavior looks extremely unstable anyway, since even a small amount of incoming matter conflicts violently with the idealized geometry they'd need. Another proposal imagines that gravitational collapse could actually spark a brand new expanding universe on the other side of the singularity. From inside, that rebirth might look and feel exactly like a Big Bang. From outside, the parent universe would just see an ordinary black hole, nothing more. Such a baby universe would likely be completely cut off causally, which makes it more of a descendant than a destination. Falling in would never get you a round trip, or even a message home. The whole idea stays speculative because it needs quantum gravity to replace the singularity with some kind of bounce, or another structure entirely, and different theories currently predict different outcomes with no experiment yet able to pick a winner. There's one more thread left to pull, and it drags black holes into the strangest argument in modern physics, one that has almost nothing to do with gravity anymore. General relativity says information can cross a horizon and vanish toward a singular end. Quantum mechanics insists information is never truly destroyed, only ever rearranged. Hawking radiation sharpened that conflict by showing black holes slowly lose mass and eventually evaporate. And if the radiation coming out is perfectly featureless, every detail of everything that ever fell in seems to disappear along with it. Modern work strongly suggests a consistent quantum theory has to preserve that information somehow. Maybe encoded subtly in the radiation, represented on the horizon, or reconstructed through a deeper holographic description, though none of that means it literally escapes through a portal. In ideas like these, a black hole's interior may not even be an independent hidden room at all. Space-time itself could simply emerge from relationships between quantum bits of information. That possibility led to one of the boldest connections in modern physics. In 2013, Juan Maldacena and Leonard Susskind proposed a conjecture called ER equals EPR, the idea that Einstein-Rosen bridges and quantum entanglement might be the same phenomenon, described in two different languages. Entanglement is easiest to picture as two coins that always land on opposite faces, no matter how far apart you flip them. Not because a signal passes between them, but because they were never fully separate to begin with. Under this proposal, certain entangled black holes can be described as connected by a wormhole. Distance in space-time and connection in quantum information may just be two descriptions of one deeper structure. That bridge, though, still isn't a tunnel you can fly through. Entangled particles let you share correlations no classical system could match without ever letting you send a controllable message through them. Once again, the portal survives the math only by losing the one feature that would have made it useful as an actual portal. Later research pushed further and found tightly controlled theoretical setups where a wormhole can actually become traversable. In a 2017 model, physicists Peng Gao, Daniel Jafferis, and Aaron Wall showed that deliberately coupling two entangled quantum systems produces a form of negative energy strong enough to let a signal pass through the bridge, instead of hitting a permanently closed interior. The trick only works in a carefully idealized setup. Both sides still need an external link to make it happen, and it doesn't turn any real astrophysical black hole into a gateway. Causality stays fully protected throughout. In 2022, a team led by Daniel Jafferis used Google's Sycamore quantum processor to simulate a piece of that same mathematics in the lab. No physical hole in space-time actually opened inside the machine. The experiment just reproduced information dynamics that share a mathematical description with a traversable wormhole, and calling that a created wormhole confuses a simulation with an actual tunnel through space. Still, studies like this show why the question refuses to die. Wormholes may be less about building cosmic doorways and more about how spacetime itself emerges from quantum information, a bridge no spacecraft could ever use, yet one that might still expose the hidden architecture of reality. Observations of black hole shadows and mergers now test gravity under conditions once accessible only through pure equations, and the measured structures line up with exactly the near-horizon behavior expected of ordinary black holes. So far, none of those observations has revealed a second mouth, a returning signal, or matter emerging anywhere from a distant exit. The honest answer, then, sits split between mathematics and nature. Black holes really can be associated with bridge-like geometries in general relativity, and certain idealized rotating solutions genuinely contain routes toward other spacetime regions. Carefully engineered quantum models can even make related wormholes traversable, but only under extraordinary, tightly controlled conditions far removed from anything astrophysical. Real black holes formed out in our actual universe are not known to offer any survivable or usable passage. Their classical bridges close too fast, their inner horizons destabilize under the smallest disturbance, and their deepest interiors demand physics. Nobody has fully worked out yet. Calling them portals isn't entirely wrong, since the whole idea grows out of serious equations rather than pure fantasy, but treating them as functioning cosmic doorways is still miles ahead of the actual evidence. A black hole might hide another region, encode a quantum bridge, or quietly give birth to a universe no traveler could ever return from. Until nature reveals a genuine exit, the most extraordinary portal in the cosmos stays exactly what it's always been, A door mathematics can draw perfectly, but one reality has never once been caught opening.